So, good morning, everyone, and thank you very much for joining us. I'm not by myself today. I've got Harm from our partners, Pentair, who supply our actual flow pumps. Harm, are you there?
Yes, I'm here, Martin.
Very good.
Can you hear me?
I can hear you.
Okay, very good.
Excellent. Pardon?
No, please continue, Martin.
Okay. So today is our presentation about fish-friendly pump technology, the technology that we've got available at ACE, and which has been developed with our partners Pentair, from which Harm is from, as well as Fish Flow Innovations. Give you a quick overview for those who don't know who ACE are. We were established in '95, so we've been in the land drainage sector for 25 years now. We've learned a huge amount along the way. We're still learning every day, of course, as we all are. We're a company of innovation. We're the first company to introduce HDP and stainless steel to the market. One of the MDs was the first guy who introduced weed screen cleaners to the market in the UK. And now we've got involved with fish-friendly pumping technologies as well. We're currently delivering some massive fish-friendly pump schemes. The main one for us that we've got live as a project at the moment is at Keedby Pumping Station. For us, that's a project over £2 million. That's for the supply and install of 6 4-QMEC fish-friendly pumps, but we also supplied and installed all the stop logs as well at the front of the pumping station, which was with divers. So yeah, we work with a great array of different organisations and outfits, everyone from the internal drainage boards to the Environment Agency to councils to the Tier 1 contractors as well. We're highly accredited. We fly through all of the PQQs that are ever thrown at us. You can see not just the qualities and the environmental ISOs that a lot of people have, but also the health and safety 18001. As well as construction online for Tier 1 contractors and the UVDB or utilities vendor base for the utilities industry. So today we're looking at the fish-friendly pumps. ACE work in particular with two different types of pump. There's the Archimedean screw pump, which is the one you can see on the right-hand side, and the actual flow pump, which is you can see the impeller of one on the left-hand side. Why do we need these fish-friendly pumps? Well, we all know, of course, that for land drainage, a lot of pumping stations, fish have to be able to migrate through. There's two types of pumping station, really. One, which is a terminal outfall. It's the last pump before the water goes out to sea. But then also you've got pumping stations which pump inland to lift the water to the next level before it's moved out by a terminal outfall to sea. So they're pumping fresh water to fresh water. So of course the terminal outfalls, we're looking particularly at eel, which are an endangered species at the moment. So we need to do our best to try and protect them. And from the freshwater side, of course, we're looking at all sorts of coarse fish that are having to pass through these systems. On the screen on the right-hand side, you can see the typical damage that's caused by land drainage, typical land drainage pumps before anyone considered fish. These are pumps that are often pumping have rotational speeds of way over 1,000 RPM, frequently up to 1,500 RPM, with the impeller and the rest of the pump has had no design consideration for any kind of fish passage. And then the right-hand side shows the kind of damage that you'd typically expect. On the left-hand side, you can see a fine screen. So the first thing that a lot of people thought was, well, why don't we just fine screen these pumping stations? But that creates new challenges as well. You can see on the image here on the left that these fish are suffering from impingement. They get drawn and stuck to the screen. That can remove scales, mucus, cause all sorts of problems for fish. And obviously the ones that are impinged and can't get off will ultimately perish there. Not saying that fine screening is not the right solution or wrong solution everywhere. It certainly has its place. For example, in water abstraction, where the flow of the river is running perpendicular to the screen, there's certainly a lot to say for, well, the fish can get past. But for terminal outfalls and land drainage pumping stations, where they're the end of the line, all the debris has to hit the screen, all the fish, everything else. Trying to screen to that kind of fine tolerance, it produces a huge amount of challenges. We think it's much more sensible to take the approach of using fish-friendly pumps. So why do pumps kill fish? Well, before anyone looked at fish, so yeah, nobody looked at the environment too much from a land drainage perspective when it was all about keeping the fields dry and looking after the crop. So it's a new thing with environmental legislation and particularly the eel regulations, which has caused us to look at it. Because in the past, when you're trying to look at pump design, you're looking at quality. You want to provide a quality product. You're looking at the speed, because the faster the pump can turn, the more compact you can make it. The more compact you can make it, the more you can drive the cost of the product down. But also, when you balance out the speed and quality, of course, you can expect high efficiency. So quality, speed, efficiency, and cost are the drivers that drove pump design for, hundreds of years. Of course, now we've got this question of fish. So where do the fish sit in? Now that raises an important question. What about the fish? What if we ignore for a second the capital cost of these products and instead take a look at how do we even make a pump fish friendly? So that's exactly what a guy called Gerard Manshanden did. So Gerard is from Fish Flow Innovations. They supply a range of products. He was originally a fisherman, specifically a freshwater fisherman, and he saw the fish populations declining because of a lot of the assets in the Netherlands that were creating barriers for natural migration courses for fish. So he created solutions including fish siphons, various other patents that he holds, but one of the most successful designs that he has is his patented fully enclosed Archimedean screw pump. So first we've got to look at the question of, if you're going to design a pump for fish, what is killing the fish in the first place? So these are some images of typical screw pumps. On the left-hand side, you can see what we call the pinch point. So the gap between the screw and the trough, which is prevalent in every open Archimedean screw. And that is where the eel can get caught. You can see in the top image, that one will have damage to its spine. And this is a typical area which causes damage. On the right-hand side, I've drawn two arrows on the screen, one showing the leading edge of a typical Archimedean screw, and one which shows another area of gap between the screw and the trough, which is a pinch point again, where fins or fish can get caught. You can see in a typical example, these are 3 monitoring results from pumping stations in the Netherlands. And you can see that typical mortality rates are anywhere between 14% and 42% mortality. Now you've got to also consider that quite a few systems, particularly in the Netherlands, you've got maybe a row of pumping stations that the eel have got to get through. So of course, if you lose 14% each time, and there's 5 pumping stations, there's hardly anything left by the time it's going out to sea. So we looked at the Archimedean screw pump and addressed those 2 key areas which are causing fish kill, and particularly eel kill. You can see the sweeping edge. Hopefully you can see my mouse on the screen. You can see the design of it. So as it cuts through the water, there's nowhere really for the eel to get caught on, to get trapped on, or for it to get damaged. You can also see that the drum is completely bonded to the vein. So you've removed all pinch points, all possibilities for fish getting caught, any areas of trapping completely removed. And of course, the whole drum rotates. To show you what this looks like, this is an Archimedean screw in action. This particular one is a 2.5 meter diameter screw. It's currently pumping circa a cubic in this image at the moment, and you can see how little the water's moving about, how nice and flat it is, and that's also very different to the open trough. And the reason for this is we can rotate our screw much slower than you can with an open trough system. We're not trying to rush the water up because there's no gap for the water to fall back down. So we can rotate it as slowly as we want, and water will still travel to the top. This provides new possibilities where we can use variable speed drives, for example, which you couldn't do on open screws before. I've noticed we've got a question. Harm, could you read out the question? Is that okay? I'll take a look at the question. Oh, sorry, it was just the webinar software. By the way, if you do want to ask questions, please do. We've got a Q&A section. You can type in any question you have. Harm and I will read it out and answer them. Back to the presentation, you can see the Archimedean screw in this image. This is also something that's very unique to us. The fact that we can install the whole screw, bearings, gearbox, motor, the whole thing in a single lift. This particular pumping station in the Netherlands was installed in a morning. So the crane turned up, the 2 lorries turned up, they started at 8 o'clock in the morning. There was a guy from the press who was supposed to be coming to have a look at it, and he wanted to watch the installation. He phoned up and said, is there any way that we can film this going in? Fishflow said, yeah, no problem, but you have to be here at 8. He'd rocked up at 1 o'clock, it was all in. He'd missed all the action.
Martin,
yeah.
Short interruption. We've got a question regarding the Archimedean screw, and the question is basically, is it possible to use a variable speed drive on open trough Archimedean screw pumps?
You can kind of use a variable speed drive on open trough screws, but the variation of flow rate that you can have is only very limited. If you run the screw too slow, then all the water starts to slip back down the system, and if you run the screw too fast, water's just going everywhere and the efficiency goes through the roof. The enclosed option allows you to have a much broader range of speed that you can operate at. We can run these pumps in theory. We've got options for operating them as slow as 2 RPM if you wish, which an open screw could never do because the water would just slip between the trough. Hopefully that answers your question. The image on the screen at the moment is of a Fike net, just to give you an idea about monitoring, because of course everything that we do, we need to make sure that it's properly monitored and tested. This Fike net is put upstream of the screw that you saw here at Halfweg pumping station. And these were a typical set of monitoring results. You can see that multiple dates, the Fike left was lifted, the fish were checked, they were visually inspected, they were put back in the watercourse. And you can see that 934 fish went through this pump. 1 was damaged. The report also goes to show that they expect it was net damage rather than anything from the pump, particularly considering that the other 933 fish went through with absolutely no problems. So you can see the mortality rate is extremely, well, even the damage rate is extremely low. Another really nice benefit of a closed screw in comparison to an open trough is we can pump into a head of water. So you can see here, I've drawn a red arrow, which would be the tipping point of a typical Archimedean screw for land drainage purposes. And the reason for that is when the water level is high, if the tipping point was low, normally a screw would start reversing and acting as a turbine. We actually put a brake on the motor so that the screw cannot go backwards. So after the screw stops pumping, it reverses, letting the water back out and the fish back out, and then a brake is applied to the motor. Our system means that it's completely sealed on this surface, so water cannot pass down through the screw. Of course, with an open trough design, even if you put the brake on, water would be passing through the system because of the gap between the screw and the trough constantly. And that is the reason why it's such a huge benefit. You can see this is an example of a 4-meter diameter screw, where we would then effectively save overall civil work height by 2.7 meters. So the whole overarching civil structure could be 2.7 meters lower than should you use a conventional open screw type screw. The savings is massive, not just in terms of cost, but also carbon. Think about the amount of concrete that you remove simply by that 2.7 meters benefit. With bells and mockets, we also had a huge benefit. Those were 2.5 meters, so we were able to lower the structure roughly 1.25 meters-ish compared to an open screw. Talking about bells and mockets, this is us installing bells and mockets to give you a sense of scale of these particular screw pumps. So each one of these is capable of 1750 litres a second, rotating at only about 22 RPM, which is much, much lower than a conventional screw would operate at. Also, we have a different pitch. So the angle of the screw is set at 26 degrees, which is shallower. And our rotation and the flight is at a different pitch than you would have in an open screw. And this is all, again, because we're not trying to rush the water up to the top. We're trying to bring the water up to the top gently. We're not trying to race the run back, the slippage of water coming back down, which means that everything can be slower, more gentle, but also more efficient. You can see here that ACE did not just supply the pumps, but we did a full M&E turnkey package. So we supplied, we were working with the crane, we installed the pumps, but also the whole kiosk that is over the top was completely designed and built by ACE and our partners. And we also supplied all the flap valves, stop logs, and M&E control system on that particular project as well. This is the finished article, one that we're extremely proud of, and we know the internal drainage board from the Lower Medway are also extremely proud of this asset. It was a huge success. It's currently being monitored by Hi-Fi, and we're looking forward to seeing the results soon. You can see the kind of volumes of water that's being pumped out. I mean, this is not the pump running flat out by any means, but when the drain is low, it can only scoop so much on every rotation. So as the drain fills up, it actually starts to pump more water as well. So there's a nice piece of footage from a drone to give you a sense of how it sits in the landscape. You can see it's very neat design, quite a modern building. Although it's quite a large asset, it's hidden into the bank quite well. It doesn't look particularly out of place. And particularly from a distance due to the green cabin, you don't really see it as much as people originally expected. So I'll ask if there's any questions about screw pumps before I move on to the actual flow pumps. Han?
Yeah, actually, there's just another question coming in, and the question is, have you got any mechanism to stop fish entering pumps, or any way to return fish if lifted back to the starting point if they are caught up in the pumping mechanism?
So if the pump is if the fish are entering the Archimedean screw, of course they will come out of the other end. If they're in the screw and the screw stops, what we do is make sure that the screw rotates backwards so it empties itself before it stops and is locked, so they can't get stuck inside. We do have fish deterrent systems because, of course, on certain pumping stations, for example, you may not want the coarse fish to go out to sea, but you do want the eels to go out to sea. So we have stroboscopic light and sound systems which can aid with that. However, I do believe there's what we should be looking at in terms of preventing coarse fish going back out to sea is using their natural instinct with allowing maybe some salinity back into the system, or some seawater back in, because of course fish, as soon as they taste that salinity, they'll be off the other direction again. And it has the added benefit of salinity will attract the eel when they're trying to migrate out to sea. There's still a lot of questions on that, but yeah, we're certainly trying to work with our partners and universities and the Environment Agency to look for solutions. So,
thank you. No further questions right now.
Is that it?
That's it for the moment.
Okay, very good. So Pentair, which is where Harm's from, yeah, they're a long-established company. They've been manufacturing pumps since the 1930s, but they're actually much older than that. They started with sewing mills and things like that, but pumps is really what they started to specialize in the 30s. They've got over 150 staff, and they're manufacturing pumps from 400 liters a second all the way up to 60 cubic meters per second, which is monumentally sized. In fact, it's actually record-breaking. This pump in the center of the screen is one of two pumps at Emoda, which is Europe's largest pumping station, which are 60 cubic pumps. One pump, 60 cubics. So they're in the Guinness World Record book for the largest volume pump in the world. You can see the facilities here. The factory is split up into the machining area, which is enclosed here. The engineering is done in these buildings. They have their own foundry, which I'll show you a bit about later. And this is their incredible fat testing facility that they have. The in-house foundry, as you can see here, is something that not every pumping manufacturer has. It surprises a lot of people, but a lot of pumping manufacturers actually design pumps, outsource all of the stuff that requires to go in the foundries, brings it back in, assembles it, and ships the pump. The downsides of not having your own foundry is you're a lot slower to respond. So for spare parts, for example, you can't produce a spare part within 2 weeks. You're stuck to the lead time of your supply chain rather than having your own production facility in-house, which means you can deliver to your customers' demands. The reason that Pentair like to have this is so particularly for the spare parts. They provide a lot of pumps also for dredging industry, which requires, because they're pumping hot, sand, salty water in the Middle East, they need a lot of spare parts and they need them fast. You don't want a dredging operation ship to be stood still for very long. But that foundry also helps for land drainage. If you need a new impeller, you know that they've got the capabilities to make it fast because they have the actual capabilities in-house. And it's something that's, that they definitely are very proud of, and it gives them a very competitive edge. In terms of the fat testing, of course, if you want to be testing your pumps, which is always recommended before they're shipped off to site, the facilities that they have at Nijhuis are fantastic. You can see that they can test pumps up to 13.8 cubic meters per hour. So they have the capabilities up to 5,000 kilowatts. So really big pump sets can be tested there. And in fact, two of the pumps for Keadby were just recently tested during this coronavirus situation. And we had to be quite innovative in the way that we carried out the fat testing. So the whole fat test was done over the internet using MS Teams. It was recorded. The consultants, as well as the project managers, everyone that was involved was able to comment, was able to ask for the camera to be moved. It worked really, really well. So we can also be smart in how we approach that. To give you an idea where the impeller came from, it's quite nice to put it next to the Archimedean screw. You can see very much the leading edge, the shape that's come in here. And the way that it works is actually harnessed from that Archimedean screw. And there's no secret behind that. It's because Gerard from Fishflow worked together with Pentair to develop this impeller system. Of course, it's not just the impeller. It's also a lot to do with the diffuser casing and the guide vanes to make sure the pump is fish-friendly. But of course, the impeller is a big part of it. Now, the main reason what makes it fish-friendly, you can see here the impeller in blue is a traditional type impeller, and of course the swept leading edge impeller of the fish-friendly. And you can see the fish friendly shown in pink, and in blue is this possible fatal collision rate for the blue impeller. The difference is, of course, that impeller comes 90 degrees, hits the water at 90 degrees or perpendicular to where the fish is coming past. At 25 degrees, even if the fish touches the impeller, it's being struck with much less force because obviously it's hitting a much smoother surface that's kind of sweeping past it rather than full on at 90 degrees. But the collision rate is reduced massively, as you can see in these two images on the bottom right. One thing to be very careful about is making sure that the whole system is not just fish friendly, but also efficient. A lot of people don't always understand that there is a direct relationship between efficiency and fish friendliness. If the pump is running efficiently, the water is flowing through it as smoothly as it can ever flow through it, and therefore it helps the fish pass through the impeller as smoothly as it can. The further away you get from your curves, the closer you get to cavitation points or vibrating situations. Also, that causes damage for the fish. The fish have a less good chance of passing through that pump. So efficiency and fish friendliness very much working hand in hand. And that's why it's important that you use a variable speed drive with the fish-friendly pump. To give you an economic reason to use variable speed drive, it's not just all about the fish, when you look at these energy graphs. So you can see the fixed speed curve on the right, so you can see single line. So the pump spins at the same speed, regardless of the head difference. Yeah. So as the head difference decreases, the amount of kilowatts required is coming down, it's reducing. And what happens is obviously at a fixed speed, as the head difference drops off, the volume of water you're therefore lifting increases. So you can see here, we've got on the curve 3 points, 9 kilowatts, 7.9, 6.4, and the flow rates will increase quite a lot as well. You can see, goes up from 1,400 cubic meters per hour up to 1,800. So as the head drops, the power drops, but actually the volume of water moved increases. When we're using variable speed, what we're trying to typically do is keep the flow rate the same. So what we get here is 3 different power curves. Each one represents a different speed. You can see on the bottom graph, the top power curve represents one speed, the middle a lower speed, and the bottom the slowest speed. So as the pump head difference is decreasing, what we're doing is slowing the pump down, but maintaining exactly the same flow rate. So here you can see we've got the flow rate at 1,400 cubic meters an hour, but as it drops down, we're dropping from 9 kilowatts to 5.9 kilowatts to 3.1. This is a direct reduction of 25% on the central point and 52% on the bottom. Now you might argue, well, yes, but at 6.4 kilowatts on the left-hand side, you are pumping a larger volume of water. So for each cubic meter of water used, maybe it's about the same. Well, even there, when you take a relative reduction and you start to look at the actual comparison, fixed speed versus variable speed, at the central point, the kilowatt usage per cubic meter of water drops to 14% and still 38% at that lower variable. So it saves monumental amounts of electricity when you're thinking you're operating big pumps with big motors using a lot of power. So it can help reduce your carbon footprint as well as getting your fish through your system. I also wanted to look at the difference between fixed speed and variable speed from the fish kill side of things. One thing that Nijhuis is extremely good at is getting all of the pumps tested. We've got in-house tests, we've got external tests, we've got tests from universities, we've got tests from different government bodies from the Netherlands, for example. So they've been tested. And through all of this testing, Nijhuis has really started to refine the knowledge of where is the pump fish friendly, where is it not? What parameters can we push it to? And how can we use this and discuss with our customers to get a pump that's optimal for their location? not every location might need a pump that's 95% fish friendly. Some might be happy with 70% fish friendly and take the capital savings. So we can have these discussions with you much more clearly and transparently than other companies, which at the moment seem to be guessing more than that they're knowing. To give you an idea, the fixed speed, you can see these brown lines. We can show that we expect 0.5% mortality, 1%, 1.5%. So each brown line represents an increase of 0.5% of fish mortality. Same on the other curve. You can see with the fixed speed, however, that of course, as you're getting close to that cavitation or the end point of your pump curve, actually you're starting to kill a lot of fish. You're starting to get 5% damage. But keeping it variable speed, because you're keeping it efficient, you're keeping your fish kill much, much lower. Still 3% for the top point, but we're dropping to 2 in the middle, and actually the bottom part of the curve is more efficient, and the fish kill is only 1%. So just by using a variable speed drive, we're reducing the fish kill by 50% at the second duty point and 80% at the third duty point. To give you an idea about the competitors out there, what we have been finding a lot is our pumps are generally a bit more expensive. They're a bit more expensive because we make them bespoke for each application. We have these kind of discussions with the client, and our knowledge of the fish-friendly aspect and where can we position it, or we can have conversations of, would you like to spend this much and have a mortality rate of that, or would you like to spend a little bit more and have a lower mortality? These are conversations that need to happen. One particular project, for example, down in Devon, we supplied 4 fish-friendly pumps for the Environment Agency, and we told them they wanted the pumps to fit in their existing canister. Their existing canister limited the size of the physical size of the pump that we could offer. And we said, yes, we can do this, but the fish mortality rate will be circa 70%. We could have ripped the canisters out, put new canisters in, and increase the size of the pump and bring the mortality rate down to 95% safe, so only mortality rate of 5%. The prices were, of course, massively different. One option, you needed a huge amount of civil work, some new canisters, bigger pumps, and the other option was simply take the old pumps out, drop some new pumps in. The Environment Agency went away and looked at the different prices, and they said, actually, this is an urban drain. There's not a lot of evidence of eel life in here. We think it's better to take the financial savings on this particular project and use that capital elsewhere, for example, on eel passes or to help the eels in other ways. This is something that we do. These are the conversations that we can have, but we also are very aware that often people are driven by cost, and what you get with cost, as I showed with the earlier slide, is a small, fast pump. And it's no different with fish friendly. And to show the effects of that, I've put this slide together. So these are 2 pumps, both been for a tender for exactly the same duty point. You can see the duty point on both of them is 1,500 cubic meters an hour with a lift of 6 meters head. You can see the 6 meters head here. So this red dot is exactly the same. The difference is the pump on the left is operating at that duty point at nearly 1,000 RPM. Our pump at the same duty point is operating at 700 RPM. You can see that for eel mortality, we're miles away from where eels start to get killed. However, the competitor pump is already at 20% of the eels are being damaged. You can see in the bottom for scaled fish, which are more vulnerable, we're seeing that we're starting to get 2% mortality rates, while our competitor is already getting 25% mortality rates. Now, if you've got 3 or 4 pumping stations in a row, there's not a lot of fish left at the end of that situation. But this is where we differentiate ourselves, our knowledge, our testing, the fact that Pentair can model this in-house. We can be much more accurate and give you really good information as to the limitations of our pumps and the balance between pump size, cost, and what your end goals are. A really nice project to show. Some of these pump technologies was down in Kent. Project called Appledore Pumping Station. Appledore Pumping Station, believe it or not, was still operating with a heavy fuel motor, a single cylinder drive that you can see on the left side. This wasn't the actual motor. I think the real one was being touched up for a museum or something somewhere, but it's exactly the same type of motor. That had failed by the time we got there, and the Environment Agency were using temporary pumps to try and keep on top of the land drainage at the time. ACE won the project because their particular layout and design of the pumping station was very challenging. The inlet sump was very shallow, and that was because the pumps that they were using at the time were an end suction pump. So the impeller was inside the building, it used as a vacuum to prime the system up, and then it starts the impeller with that old diesel motor, and the pump flow goes through. With the end suction pump and that shallow sump, it becomes quite tricky to place a submersible pump in the sump, unless you allow the drain levels to be higher, which in Kent you can't, because all of a sudden everything goes out the window when you need a half a metre extra water in your drain. The other option is break out the whole pump sump, make it deeper, excavate down into it, reline the pump sump, and then you can put your submersible pump in there. Our competitors didn't have an answer. They said, yeah, we can either make the drain deeper or we can break all the concrete out and make it, but that's the only way. ACE came to the table with our partners Pentair and said, there has to be another way. There is a way that we can use our fish-friendly pumping technology on this particular station. Using an FSI, a formed suction intake, you can see that this shape here, this wedge, we believed that we could model the pumping station to make sure that we didn't have to have the sump depth that you would normally do with a submersible type axial flow pump. What this does is it guides the water into a kind of trumpet shape and then into the pump. And we could model that all using CFD, which is what the image is, but there's a full report, quite a few pages thick, which shows exactly where we can draw the line, where the limitations are, how we can do it, what the design of the FSI needs to be, and that, yes, we could achieve all of the duty points at all of the levels with a fish-friendly execution by putting this solution forward. So we had a solution that nobody else had. And this is something that Nijhuis can only do because they have an internal CFD team. So they have a whole department, and their department in Winterswijk in Holland is actually Pentair's global center of expertise for CFD. So they do the CFD for all of Pentair's pumps that are manufactured in China, in America, all of them. So really a phenomenal team, which can show you exactly where the edges are, exactly where the tolerances are, exactly how the water is going to flow through the system. And during commissioning, it all proved to be exactly as we expected. I've noticed that we might have a question, Harm, is that right? We've got a question asking, can you please explain the typical applications that these pumps are used in? I presume... Oh, Harm answered that privately. Typical applications, both of them are, of course, for land drainage purposes. We generally tend to say the Archimedean screw. If you've got two static levels, then there's no more efficient way of going for it. Does change a little bit depending on the diameters. Sometimes if the tidal range isn't too much, it can be different. Axial flow pumps are excellent at taking up the level changes because, of course, their duty points can change quite a lot throughout a range and throughout the curves. So yeah, this is Appledore and the submersible pump being dropped into these canisters for that project. This is Kenwith, a project down in Devon. We supplied 4 700 litre a second pumps, 75 kilowatts down there. And you can see on the right hand side another critical point for fish-friendly pump applications. You need to use HDP flap valves. There's no point getting a fish, lifting it up, it's all safe, flying through the pipework, and then it knocks its head on a big, heavy old cast iron valve. It just doesn't work. You need to have something like HDPE, because it's buoyant neutral, it's light. You can see in the video here, it's open at 90 degrees. There's no way it's preventing any fish from getting through. So it's an important consideration. We delivered the flat valves as well as the pumps on this project for the EA. This is another example where we used our submersible pump technology. This is out on the Humber. So for the Ouse and Humber drainage board, they had 2 land drainage pumping stations. This is the slightly bigger one, and literally, less than a mile down the road is the other one at Blacktoft. Ace didn't just supply the pumps, we supplied the pumps, the canister, the kiosk, the panel, also the big non-return valve at the end of the drain, with a fish-friendly flap on it on both pumping station sites. So it gives you a nice flavour that we can provide a holistic package.
Martin, we've got a question coming in. It's regarding, I think, the previous project, Appledore, and the question is, how did this pump deal with silt? Does it draw through, or do you need to maintain the sump? So maybe that's interesting to answer in relation to the FSI, and perhaps you can also make a reference to the Kenwith project.
Yeah, that's a good point. In terms of the silt, with the CFD modelling, we can actually also look at suspended solids. So with the Kenwith project, I'll go back a few slides, that's this one. There was a huge amount of silt building up into the sump. The sump had all rectangled square edges. Nobody had clearly looked at it from a hydraulic point of view very much. But basically, we did a full CFD report at Kenwith specifically for the reason of trying to maintain the suspended solids as much as possible to make sure the pump is pumping them out and they're not able to settle. We suggested benching options, different profiles that they could put into the sump to reduce this. Unfortunately, for cost reasons, I don't believe they did all of it, but they did put some benching in some key places, and it seems to be working. With Appledore, silt was less of an issue because it's a chalk river, so there isn't too much in there. Having said that, once again, with the FSI, it did mean that, once again, we're keeping the silt suspended, and it flows through the system. It might get caught behind the FSI, but it's not a problem because, of course, you're drawing the water from the front. Would you have anything to add to that, Han? Han?
No, I've got nothing to add, Martin. I think you answered that perfectly. So it's mainly a matter of keeping sufficient speed in the intake of the pumping station, so it will draw the silt with it through the pump, and that's one of the main design criteria where we would look at in sites where the siltation could be a potential issue. So that's maybe a small addition to that.
Yeah. Any more questions?
No further questions at the moment.
Okay, very good. Interrupt me when the next question arrives. So this is our current biggest project, Keedby, where we're supplying 6 4 cubic pumps. As I said, 2 of them were recently tested over MS Teams. And this gives you a sense of scale when you see the little person stood next to the huge pump. This is a particularly challenging project because the existing pumps, again, like Appledore, were end suction pumps. So the impeller would have sat where I'm circling the mouse at the moment. And this is almost a form suction intake for the water to get drawn up into the impeller. With the impeller system up here, of course, you're operating with a vacuum pump to prime the system before you start the impeller. The Environment Agency were keen to remove the vacuum pump system because they're renowned and they've experienced a lot of maintenance problems with it. So what we offered was a pump with a submersible impeller. So of course, doesn't need its self-priming, or it doesn't need priming because the impeller is below the water level. And then once again, a formed suction intake which was designed with the CFD to ensure the water was able to flow up. We weren't going to get cavitation issues and those kind of things. We were really clever on this particular project with a few points. There was a lot of challenges. One was in terms of weight. For example, the existing gantry crane that was within the building had a weight limit of 5 ton. Using induction motors, because these are big motors, 330 kilowatts, with an induction motors, you're looking at 12 ton just for the motor. So we were looking at the project and thinking, well, it's going to cost a lot of money if they have to replace the crane. Are there any alternatives? And we have a motor alternative using permanent magnet drives, where we were able to reduce the weight of the motor to only same power, same efficiency. In fact, it's an IE4, so probably higher efficiency, producing 10,000 Newton meters of torque, 330 kilowatts, only weighs 3.2 tons. And by doing that, it meant that the whole gantry crane inside the building could be repurposed, it could be kept, they didn't need a new one. So huge savings to be made there. And that was, I think, with the fish friendliness, the confidence that we could give in that was all contributed us to ACE being awarded the project. It's one we're very proud to be a part of, and we're quite excited to start getting the pumps installed. We can also do horizontal pumps. This opens up a whole new board game for a land drainage pumping station. So when you think about where the efficiency losses are, it's on pipe bends, it's on pipe frictions, it's valves that you have in your system, that kind of thing. You remove a huge amount of them by having a horizontal pump. You can see there's nowhere really for efficiency losses through the system. There is a non-return valve, of course, so you'll get some head loss there, but very, very efficient design solution by having it horizontal. It also produces a very low construction. So when you're looking at particularly sites that might be in urban areas, somewhere which could be in an area of natural beauty, if it's in a park, for example, and you want the visual impact to be as low as possible, of course, with a horizontal system, you can actually put the pumps underground, as you can see here. This is not just a concept, this is the completed land drainage pumping station in the Netherlands. You can see here how low the whole thing is. The road deck is up here, is level with the crest of the bank. So yeah, as soon as you're maybe a kilometer away, you don't see it anymore. So very, very neat visual concept. The pumps here, how big were these, Harm? Were these 4 cumecs a second?
Yeah, Martin, that's about the capacity.
Yeah. So there was 4 cubic per second horizontal pumps that were installed here. You can see, it's completely in its own casing, and also to help lift it in and out. The way that it's installed is there's a galvanized puddle flange at either end, which is cast in situ. So these are all set out with chocks. You cast the puddle flange in, and then the pump seats against that puddle flange with its own weight. So you can lift it out without having to get in and undo bolts and nuts and things and everything. You can literally attach it to a crane hook and lift it straight out. The only thing sealing it is its own weight. It's a very clever concept. As I said, it opens up new avenues, ones that we're really keen to explore, which is the possibility of a lower carbon, or very possibly even a full carbon neutral pumping station. This is something that's not really been thought of before, but imagine if a pumping station can generate enough power to offset itself completely. It might even be able to generate enough power to offset itself and become carbon negative. By pumping at horizontal, of course, if you imagine on the left-hand side of your screen is your intake, and on your right hand of the screen is your outfall level. It's the C, essentially. This would only really work on tidal systems. Then you're pumping water when the sea level is higher than the drain. However, as soon as the drain level drops, you can actually, normally a lot of land drainage pumping stations on the coast have got a gravity sluice. And that might be a flat valve with a penstock, or sometimes it's a big sluice gate. At Keadby, for example, there's 6 of them underneath the building, all vertical penstocks, and you're just letting the pumping station or letting the water flow out by gravity. You can harness this now. We can send the water through the horizontal pump. That rotates the permanent magnet motor that can be in there, which can be switched from using energy to producing energy. So we can then actually produce energy from all of the water that's flowing through. When you think of a lot of our coastal pumping stations, many of them only actually pump for 2, 3, 5 weeks in the year, maybe. When you actually add up all their pumping time, imagine if you could harness back all of that energy that we're losing with gravitational flow. It's a real, benchmark, we think, but we do need to find a site and a project where we can harness this technology. You'll get a pumping station that's low, visually almost invisible, that generates power and completely makes it carbon neutral. It's got to be an attractive proposition. Rounding up, overall, why would we go with our pumps? Well, the capital costs are a little bit higher. As I said, we're not ashamed about it. We look at quality. We want to be fish friendly. We want to be the top of our game. We don't want to fight on price. We want to make sure that you get a product that does exactly what we tell you it's going to do. In turn, it means you've got a better OPEX, or lower operational costs. With our Archimedean screws, they're only doing 20 RPM. Those bearings last 15 years easily. With the actual flow pumps, we're only operating, for example, at Keadby about 300 RPM. So when you compare that to a pump that traditionally pumps 1200 RPM, you can tell logic dictates your seals last longer, your bearings last longer, everything's got a longer shelf life because you've bought a bigger asset that operates much slower. So you're increasing your asset life, you're doing less maintenance, and therefore we're convinced that on the Totex position, so your total life costs, the products that we have available will be much better than the products that were procured probably from the 80s into the 90s, where speed and capex was really the driver of everything. To give you a hint, go and look at the pumps from the 1950s and the 1960s and the 70s that we still have in operation today. They're in operation today because they're big, they're slow. Actually, quite a lot of them are fairly fish friendly, and they still work. What we're finding is we're replacing a lot of pumps that were installed in the 80s and 90s, where people were trying to speed them up further, make them smaller and smaller. And of course, it has an implication in the life cost and ultimately the amount of maintenance you need to do. ACE can't just supply the pumps. We also, as I said earlier, do full installation and turnkey services. So we can supply the pumps, the panels, the non-return valves, the weed screen cleaners, full M&E package if it helps you. Not everybody wants that. We're happy to just supply a pump, but a lot of people see a lot of value in us taking on the whole project. Don't forget, we also do big penstocks, big lock gates, WASTOP, excellent non-return valve. These are actually being used in conjunction quite frequently with the fish-friendly pumps for the outfall. The weed screen cleaners in the top right, we have them at some of the UK's biggest pumping stations, at Crossons, for example, in the northwest. 30 cubic stations. We've got 4 500 kilo, 1.8 meter Landestry grab units there. I hope you enjoy the presentations. I will take any questions. Harm, do we have any questions?
Yes, we've got one last question coming up. So the question was about horizontal pumps. And the question is basically, can these pumps also be used as flood defense along the canal? And the concern behind this question was more or less when the river levels would be high and if the stormwater needs to be drained from the cities. So in answer to that question, yes, the horizontal pumps can very good be used for this type of application. I mean, it's intended to be pumping against a pumped head, so the river level can be significantly higher compared to the drain water level. And the pumps, horizontal pumps, can be used for this. And the background behind the question was also because it would be nice in this particular application to have the pumps below road level, and this is again possible. So in the Netherlands, we've got already some specific applications for this pump, exactly in the situation as was explained in this question. So the pumps, they can be used completely hidden away, for instance, below the road or below parking lots, etc., to drain any type of water to higher water bodies such as a river. This is a possibility, and also a small addition maybe to the OPEX and CAPEX comparison that you made. Another advantage that you see when using, for instance, this horizontal type of pumping applications is generally that there's also a saving in the CAPEX, because it eliminates basically the need for a pumping building on top of the pumping station. So it's all in ground, and also for instance, the generated heat by the motors, etc. They're all being maintained in the ground and basically controlled by the water flow of the pump.
Very good. The question's just been elaborated on a bit further. That specific pumping station with the horizontal pumps I showed, Harm, is that pumping into a river, or is it for storm applications after a rainfall event? Can you tell us a bit more about that?
Yes, so actually at the moment we've got several types of installations. In some cases, because the pumping station shown by Martin is showing one application of a relatively big pump with diagonal of cross-section of 1.8 meters. But we've also got installations with smaller pumps, such as 500 millimeter cross-section pumps, 800 millimeter cross-section pumps. And in some applications, these pumps are also used for basically for creating more or less of a current in the canals of Amsterdam, for instance. They want to maintain a certain amount of flow in the canals to avoid the water getting smelly, to refresh the water. So in some places, they've got these types of pumps installed with a very low head of basically only 20-30 centimeters of head to maintain a certain flow in the canals. So aside from a typical drainage or flood control situation, such as the one that you're showing right now, it's just draining water and pumping it actually in this case to the Markermeer, which is the part of the central lake in the Netherlands. It can be used in all similar to basically your normal vertical types of pump installation. It just brings several advantages, which in some cases way bigger than in other cases where vertical pumps can be a good solution. But it's very fish friendly because of the elimination of bends, and because it eliminates bends, it's also got less dynamic losses. So generally, this type of pumping station is very energy efficient and very fish friendly as well.
Excellent. I think I've got another one for you, Harm. The question is, although these pumps are understandably large for the purposes they're being used for fish friendliness, fish friendliness is required at much smaller volumes as well. Do you have solutions for the smaller ones? Now, I know I've been in discussion because you are developing a smaller pump. The question is actually asking about 20 to 50 litres a second. But do you have any indication on the kind of range that you'll have available on the smaller pumps that you're developing at the moment?
Yeah, yeah, that's an interesting point. It's certainly a point I would like to add to the end of the presentation anyway. So good timing for this question. Yes, indeed. So as you were saying in the introduction, currently our land drainage, fish-friendly land drainage range more or less starts at 400 liters per second. And at the moment, we are working on a new fish-friendly pump range, which is specifically designed for the smaller flows. And at the moment, it's fully in development. And we've actually built the first prototypes already. But the range will more or less start, also depending from the head, at 50 liters per second. So maybe for some applications, some heads, the 20 liters per second that is referred to in the question will also be possible. So in case you've got this type of application with smaller flows, please send your inquiries to Martin, and we will come back to them and inform you whether this will be possible with our new pump range that is in development.
Excellent. I think that's about it, unless anybody has a last question they'd like to ask. Okay, I hope you enjoyed the webinar. If you do have any questions, please don't hesitate to contact us. Our telephones are still open. There's still a skeleton crew of people here at ACE to make sure that we can ship the flat valves, the wire stops for all of those key sites for utilities industry, as well as, of course, land drainage for any emergency works. So use our telephone number that's on your screen now, email address. If you want to ask me directly, don't hesitate to call and ask for Martin. Yeah, and hope you have an excellent Friday and make the most of the weather and everything else as this pandemic is panning out. Thanks a lot for your time.
Thank you, everybody.
Thanks, Harm.
Thank you. Oh, Martin, just a second. No further questions, just some positive comments, so that's good to hear. Thank you all.
Oh, thank you for the positive comments. Okay, bye.